Jnanam paramam dhyayam. Knowledge is supreme.
Welcome back, students. We were looking at approximating any higher order system as a first order plus date time, and there are, broadly speaking, two ways of approximating a higher order system, any higher order system, into first order plus date time. Depends on what information we have about the process. Either we may have the actual plant from which we can generate some data. So we may have raw data of the output variable as a function of time, or we may also have the transfer function representation of the system which is of higher order. So we'll see in both these cases how do we approximate this response as a first order plus date time. So we'll start with the case when we have the actual transfer function between the input and the output. So what we have is a higher order transfer function which we want to approximate into first order plus date time model. So what we are essentially doing is we are converting this as Kp over tau s plus 1 e raised to minus Td. So we need three unknowns. What is the ultimate gain? What is this time constant, and what is the dead time, given the fact that we have the transfer function for this process. So there are two methods of doing this. The first method is based on Taylor series expansion, and the other method is Sujit's half rule. In both the cases, the notion of Kp is the same. So Kp is gain between input and output. So for the given transfer function, whatever is the gain between input and output, same gain would get transferred to the final approximate form. The second term is how do we get tau. So tau, as I had said, it's sort of a representation. It is a mathematical entity which just approximates or matches the given response with this approximated model. It does not have a direct physical significance. So when we talk about Taylor series based method, approximation, tau is taken as the dominant time scale of the process. And by dominant we mean the slowest time scale. So if our process transfer function was something like this, s plus 1 to s plus 1 all the way up to 5s plus 1, then tau 1 is equal to 1, tau 2 is equal to 2, and tau 5 is equal to 5. So the slowest mode out of this is coming from this 1 over 5s plus 1. So in that case we will be taking tau as 5. So it is the dominant or the slowest dynamic mode is taken as the time constant or tau. In the case of Sujit's method, what we take is tau is taken as dominant time scale plus half of the next dominant one. So we are not relying only on the slowest time scale, but we are looking at the top two slow time scales of the process. And in that case, for this particular example, what we would be getting is this tau will be equal to 5 plus half of the second slow. So if it is s plus 1, 2s plus 1, 3s plus 1, 4s plus 1 times 5s plus 1, it will be half of 4. So in that case, we will get tau is equal to 7. So that way the tau obtained for the same transfer function by using Taylor series expansion or Squigster's method, they are going to be different. So the Squigster's method will give you higher tau value. And then the last parameter which we want to get is TD, which is the dead time. So the way we get the dead time is, let's say if we look at the Taylor series expansion based method, so we look at the remaining transfer function after we have removed tau. So in this case, the remaining transfer function was s plus 1, 2s plus 1, 3s plus 1 and 4s plus 1. So we approximate it as e raised to minus TDS. The way we do it is, we try to write each of these. So let us say if I take s plus 1, this is approximately equal to e raised to power 1s, because if you take Taylor series expansion of e raised to s, it will be 1 plus s square over 2 factorial. So this is approximately equal to e raised to s, which is equal to e raised to minus s. So similarly, you can write that 2s plus 1 will approximate to be e raised to minus 2s. So this entire time, for this particular example, it will be equal to e raised to minus 1 plus 2 plus 3 plus 4s, which is equal to e raised to minus 10s. So your TD will be equal to 10 in this case. So to get the dead time, you just approximate the remaining transfer function as a Taylor series approximation. In terms of Squigster's method, we follow the same approximation procedure. The only difference is this 1 over 4s plus 1 is approximated e raised to minus 4s. But in terms of calculating tau, we have already used half of this contribution. So that 2 out of that 4 was taken as tau. So in this case, the contribution to dead time is also taken as half. So it will be half of 4, so it will be 2. So based on this, the actual TD here will be 1 plus 2 plus 3 plus half of 4, so which comes out to be 8. So the dead time in the Squigster's method will be smaller than what you get from the Taylor series approximation. So for this particular example, so if GS was equal, let us say equal to 1 over s plus 1, 2s plus 1, 3s plus 1, 4s plus 1, 5s plus 1, if this was the transfer function, what we get is gain will be equal to 1, because the gain gets transferred directly. For the Taylor series based approximation, we get 1 over 5s plus 1 e raised to minus 10s, and for Squigster's method, we get 1 over 7s plus 1 e raised to minus 8s. So both these are approximations for this transfer function, and if we plot a step response of this particular transfer function, you can see that the response is shown here. The green line represents the actual response where the step change was given at time t equal to 10, and you can see that both these models are approximating the behavior fairly with a good match. You can see that the red line is closer to the real response, and that corresponds to the Squigster's rule. So it's a more empirical method which was developed by Professor Sujit, and by just taking the second dominant scale and increasing the tau, and while reducing the dead time, it is able to match the response in a much better way. Next, we look at if we don't have a transfer function representation of the process, but we have the actual process, and how do we come up with this first order plus dead time approximation. So in that case, what we do is known as step testing of the plant. So let us say we are interested in the relationship between, so we are interested in its output is y and input is u, which we are going to represent as first order plus dead time model. So what we do is, in the given plant, we make a step change in u, let us say of magnitude a, and we record the response of y as a function of time. So what we are going to get is a response of this type. And when I say yt, it is always a deviation variable. We give a step change when the plant is at steady state, and we record the response as time goes on increasing away from this particular steady state. And the typical response what we will get will be of a sigmoidal nature. It will start at 0, take some time, and then reach the final value. So from this response you can record, and then from this response we would be able to find the values of Kp, tau and Td. So in order to get Kp, it is the gain of the process. So it is the total change in y divided by total change in the input, and this is at the final steady state. So for this particular example, the total change in y is going to be this. So the ultimate value is this. So the total change in y is this, is delta y, and delta, let us call it as b. So the gain in this case will be equal to b over total change in input was a. So the Kp will be equal to b over a. So that way we will be able to get the gain of this process. Let us now look at how do we get tau and Td. So let me redraw the same figure again. So in order to get tau, what we do is we take slope of this sigmoidal response at the inflection point. So we draw a tangent at the inflection point, so which is somewhere here. So let us say that tangent looks like this. So this is the tangent at inflection point, and let us say its slope is equal to s. So from the first order dynamics lecture, you should remember, you should recall that the slope of the first order response at time t equal to 0 is given by a Kp over tau. So we'll make use of the same relationship. So in this case, slope is s and AKP is nothing but b. So b over tau. So we'll write tau as b over s. So the tau value which we are interested in is equal to the ultimate value of output y divided by the slope of this tangent at the inflection point. And then lastly, we are now the only thing remaining is the dead time. So we take whatever is the intersection of this tangent at time to the time axis. So this intersection we take as TD. So this will be our dead time. So if we have the actual process and don't have a transfer function, then using this method we would be able to approximate this process as first order plus dead time. So this is a very common way any real plant data would be analyzed and converted into first order plus dead time model. Now just I would also like to make a small note that sometimes the order of the system is very high, and in that case running a step response and trying to get the final output, it takes a very long time. So in that case the typical example of this would be let us say if there is some we are interested in finding the transfer function model between the product purities of the distillation column and the feed composition. We had seen this as a motivating example, and the order of the system is equal or is of the same order as that of the number of stages. So if the column has large number of stages, this becomes a high order 20-30 dynamic model, and it takes a very long time to settle. So the response would typically, in such a case, if I say xd versus time, the response would be so slow that it will take a long time of the step testing to reach the final steady state. So in that case, most of the time these models would be used to make the initial predictions about how the system responds. So what we consider is we just consider the response only up to this point, and what we say is it is similar, or we approximate it not as a first order plus dead time, but we consider that the response is like some dead time followed by a ramp. So we approximate this as a ramp rather than a response of a first order process. So in that case this is known as a first order plus integrator. It is not a first order lag, but it is a purely capacitive process for which the transfer function will be Kp over S e raised to minus Td. So in this case the only two things which we are interested in is what is the dead time and what is the slope here, which would give the value of gain Kp. So especially this type of approximation is made when the system is really of higher order and it does not reach the final value in a foreseeable or whatever is your prediction horizon. So to summarize, we have seen that in order to get a higher order process, it's typically a series combination of multiple first order systems, and therefore they are typically overdamped, and rather than analyzing each of those orders separately, we typically convert them or approximate them as first order plus dead time model, and that is the model which we will be using to make prediction or design a controller for that particular higher order system. And then that FOPDT model can be obtained either as an approximation of the original transfer function which we have generated, or it can be obtained from the experimental data or the real plant data. So we'll stop this lecture here, and in the next part of this lecture we'll look at the numerator dynamics. Thank you.